Welcome back, everybody. In this lesson, we are going to look at conditional and biconditional statements. Now, before we get started, I'm going to be honest. Of all the topics that I teach, of all the math classes that I teach, this topic, conditional and biconditional statements, is one of the trickiest topics to teach and help people understand. If I could choose one lesson that we could all be in person for and look face to face, this would be the lesson. This is a tricky one, but we can get this, and you can get this. I'm going to go through the explanations of these topics kind of slowly, and I'm going to encourage you to rewatch these explanations until they make sense. And we can meet online if you need to, but we're going to get there. The upside is that if you can understand conditional and biconditional statements and logic, then that means that you have really arrived. That it means that your understanding of the logic principles that we've laid down have really taken hold, and you've really made some good ground. So enough about that. Let's get started. Okay, so let's start with conditional statements. A conditional statement is a statement in which one statement's truth implies another statement's truth. We sometimes call this an if-then statement. If P, then Q. But more formally, it means if P is true, then Q must also be true. So what this means is that the conditional statement P implies Q. It's true when Q is true when P is true, or when P is false. So let's make a truth table and map this out. Let's let P be the statement you win the lottery. Q is the statement you will pay a large amount of money in taxes. Okay, so our truth table then will have P and Q and the conditional statement P implies Q, or in other words, if P, then Q. So as always, we're going to have true, true, false, false for our P conditions, and Q will be true, false, true, false. Now, what will be the outcomes for P implies Q? Well, P is true and Q is true. That is to say, if we do win the lottery, will we pay a lot of taxes? Yes, that is true. What about row 2? If we win the lottery, paying a lot of taxes is false. That is to say, can we win the lottery and not pay a lot of taxes? No, that is not true. That's the case that violates this. If the conditional statement holds, then the truth of P means that Q has to follow, and it doesn't here. P is true, but Q is not. Therefore, the conditional statement is false. In other words, we had P, but not Q. Now, the last two cases, if P is not true, but we have Q, that's still true. That is to say, if you don't win the lottery, but you pay a lot of taxes, is that possible? Yeah, that's possible. A lot of people pay a lot of taxes without winning the lottery, so that statement is true. And what if they're both false? What if we don't win the lottery? Does that mean we might not pay a lot of taxes? Yeah, my kids did not play the lottery and they don't pay any taxes. And so that condition is true. So conditional statements, P implies Q or if P then Q, will typically have three trues and a false. The only one that isn't true is when we do have P, but we fail to have Q. That's the one case that violates the conditional. Now, everything we're going to do today is based on this idea. If that makes sense, keep on watching. If not, you might want to rewind and just go through that explanation one more time. Now, related to conditional statements are the three cousins of a conditional statement, and they are the converse, the inverse, and the contrapositive statements. Let's look at each of these three. Again, we're going to start with P and Q with the same four conditions. I'm going to leave our truth tables column of the conditional P implies Q here. In fact, I'm going to label that conditional. But let's map out a few other cases on this truth table, and I want you to make an observation. The first one, let's create the converse Q implies P. Okay, so this is still a conditional, but it's asking the reverse. does the existence or the truth of Q mean that P is also true? Let's go to row 1. Q is true. Is P also true? Yes, it is. And so we can say that that row is true. Row 2, Q is false, but P is true. What's the outcome here? Well, does the truth of Q imply the truth of P? It doesn't matter because Q isn't true. And if Q isn't true, it doesn't matter what the outcome of P is. And so that one is true. Row 3. Here, Q is true, but P is false. So did Q imply P? Did the truth of Q mean that P also had to be true? No, it didn't. Here, Q is true, but P was not. And so that one fails. This statement is false. And our last one, does the truth of Q imply the truth of P? Well, it doesn't matter because Q is false, and so this one is going to be true. So here again, this is a conditional statement, but it's in the opposite direction. So we got 3 trues and 1 false. But since this one was going in the other direction, we call this the converse. So going back to our original simple statements, if P is winning the lottery and Q is paying a lot of taxes, the conditional statement would be, if you win the lottery, you will pay a lot of taxes. The converse statement would say, if you pay a lot of taxes, then you must have won the lottery. And that, of course, is a different statement, which is why we got different outcomes. Now let's look at 2 more types of statement called the inverse and the contrapositive. The inverse is the statement that not P implies not Q. Contrapositive is not Q implies not P. So I'm going to make another table, but this time along with P and Q and their normal possibilities, we want to note what the negation of P and the negation of Q are. So we're going to have a column here for the negation of P, which is of course switching all of P's entries. And I'll have a column for the negation of Q, which reverses all of Q's entries. Now the first case I want to look at here is what we call the inverse. Not P implies not Q. So in terms of the lottery and taxes, this would mean that if you don't win the lottery, does that mean that you won't pay a lot of taxes? Well, no, not necessarily. Let's break this down. What we need to look at here is, does the truth of not P mean the truth of not Q? Let's take a look. There's not P, and it's not true, so this one's automatically going to be true. Row 2, does not P's truth imply not Q's truth? No, it doesn't matter because not P isn't true, and so this row will be true. Row 3, does the truth of not P imply the truth of not Q? This one fails because not P is true, but not Q doesn't follow, and so this is the row that will be false. And in our last row, does the truth of not P imply the truth of not Q? Yeah, it does, and so we have a true statement there. And again, we call that the inverse statement. So I want to point out that if our original statement is P implies Q, the converse reverses P and Q, but the inverse negates both P and Q. P implies Q is our conditional statement. The inverse statement is that not P implies not Q. What I want you to notice here is the inverse statement does not give the same results as our conditional statement. That is to say, if you win the lottery, you will pay a lot of taxes. Is that the same statement as if you don't win the lottery, you won't pay a lot of taxes? No, those aren't really the same statement, and we can see that because we didn't get the same results on our truth table. Now, you'll notice that the inverse and the converse did give the same results, and so that means that these 2 statements, not P implies not Q, and Q implies P, are actually the same. But here's the result I really want you to observe. Let's look at one more statement called the contrapositive. Not Q implies not P. Let's build our column here. Does the truth of not Q imply the truth of not P? Well, let's go look. The truth of not Q, well, not Q isn't true, and so it doesn't matter what happens to not P. We're just fine right here, it's true. Row 2, does the truth of not Q imply the truth of not P? No, it doesn't here because not Q is true, but not P doesn't follow, and so this entry is false. Row 3, does the truth of not Q imply the truth of not P? Doesn't matter. Not Q isn't true to begin with, so it's moot. And does the truth of not Q imply the truth of not P in row 4? Yes, it does. They're both true, and so we get a true statement. Now, what is the contrapositive actually saying? Again, P means we won the lottery. Q means you're going to pay a lot in taxes. So what this is saying is, if you don't pay a lot in taxes, does that mean you didn't win the lottery? Yeah, actually, that's true, right? That means the same thing. It means that if you aren't paying much for taxes, you must not have won the lottery. And if you look at our truth tables, you'll notice that the outcomes of the conditional column, the conditional statement, true, false, true, true, are the same as the contrapositive, true, false, true, true. That means that P implies Q is the exact same statement as not Q implies not P. If you win the lottery, you will pay a lot of taxes. That's exactly the same statement as saying, if you don't pay a lot in taxes, then you must not have won the lottery. So there's two relationships to observe here. The inverse and converse statements were equivalent, and that's fine. But the one I really want you to notice here is that the conditional statement and the contrapositive statements are equivalent. That's what we're going to focus on next. We can generalize that and say that any conditional statement P implies Q is equivalent to its contrapositive statement not Q implies not P. That is to say, we're always going to get the same results regardless of what the statements Q and P are. And so we can reword statements according to the contrapositive. I'm a big Pink Floyd fan, and there's a reference to this in the album The Wall. And if you're a Pink Floyd fan, you might recognize this. But suppose if you want to have some pudding for dessert, then you have to eat your meat. That's a conditional statement. Well, let's break that down. In order to have any pudding, then you must eat your meat. That is to say, that aligns with if P, then Q, where P is have pudding. If you want to have pudding, then Q, you have to eat your meat. Okay? That's the conditional statement. What would the contrapositive be? Well, let's break that down. If P, then Q, that is to say, this is the representation of P implies Q, where the only false outcome would be somebody who gets to have pudding without eating their meat. But what would the contrapositive be? The contrapositive will be the reversal of this and both negated. Not Q implies not P. Now let's write that in words. That means that another way to say that same statement is not Q. If you don't eat your meat, then no P. You can't have any pudding. And that conveys all the same conditions. In order to have pudding, then you must eat your meat. And if you don't eat your meat, then you can't have any pudding. That would be the contrapositive statement. Let's do one more. You must be 21 in order to legally buy alcohol. That is certainly true, so let's put that in the form of an if-then statement. Now be careful, don't just write things in the order they appear in the sentence. You have to ask yourself which thing actually depends on the other. What's the if and what's the then? So in this case, we would say, if you want to buy alcohol, then you must be 21, right? If we frame it in that way, then we can see that the P, the original statement, is buy alcohol. And the Q statement means that you have to be 21. If you want P, then you have to be Q. And here again, you can see that the only false condition here would be a case where P is true, but Q is not. The truth of P would not imply the truth of Q. That is to say, the only case that would violate this conditional is somebody who does buy alcohol, but is not 21. And of course, that shouldn't happen. So what would the contrapositive be? That's the question. Well, the contrapositive, without even thinking about our context here, will be the reversal of P and Q and negated. So instead of P implies Q, we're going to say not Q implies not P. Now what would that statement be? Not Q means if you're not 21, then not P. You can't buy alcohol. And you might say, well, that's just the same thing said in a different way. Yes, and that's exactly the point. Here we're saying it from a positive standpoint. You do want to buy alcohol, you must be 21. Here it's from a negated and reverse standpoint. If you're not 21, then you can't buy alcohol. From a logic standpoint, those two are exactly the same. Okay, for a little bit of practice here, why don't you pause the video and write the contrapositive statements to each of the following. The first one, to earn a degree, you must pay your tuition. And the second one, to order off the children's menu, you better be 12 or younger. Go ahead and pause, write the contrapositive to those, and unpause to check your answer. Okay, for our first one, to earn a degree, you must pay your tuition. What's the conditional statement? P implies Q, or in other words, if P then Q, what are our Q and P? Well, P would be the earn a degree, and Q is pay tuition. If you're not sure about those, try reversing them and see if they make sense. That is to say, if you pay tuition, does it mean that you'll earn a degree? Not necessarily, so that would mean that they're backwards. So P is earning a degree and Q is paying tuition. Then the contrapositive is found by switching the order and negating both. So the contrapositive would mean not Q implies not P, and we've already shown that whatever this says is the same statement. So now let's just translate this. Not Q, that is to say, if you don't pay tuition, that implies not P, you won't earn a degree. And there it is. And that is the exact same statement that you were given, but in contrapositive form. The original statement was in terms of positive things. You can earn a degree if you do pay your tuition. This is in terms of their negations. If you don't pay tuition, then you won't earn a degree. Our second one, to order off the children's menu, you must be 12 or younger. If one thing, then another. If you wish to order from the children's menu, then you must be 12 or younger. P is being played by ordering from the children's menu, and Q is being played by 12 or younger. So what will the contrapositive be? The equivalent contrapositive statement will reverse P and Q and negate them both. In other words, not Q implies not P. We'll get an equivalent statement. That is to say, not Q. If you're not 12 or younger, then that implies not P. You can't order off the children's menu. Same statement, but said in contrapositive form. Okay, well, let's move on now to biconditional statements, or in other words, if and only if statements. And you'll sometimes see this represented as IFF. A biconditional statement is a statement in which one statement's truth implies the other statement's truth and vice versa. That's the part that's new. It means that one thing is true if and only if the other one is also true. So for example, let's let P be the statement, you've been to New York City, and Q be the statement, you have been to the most populated city in the United States. Let's make a truth table for the biconditional, which we represent with a double arrow for P and Q. Okay, so we're going to start with a P column and a Q column, and our normal 4 rows given our normal truth table conditions. And this time we're going to test the biconditional. P implies Q, that is to say P implies Q and Q implies P. So if you have been to New York City, if P is true, does that also mean that you have been to the most populated city in the US? Yes, it does. And in fact, T is true and Q is true, and so we would have true. What about row 2? P is true, but F is false. Biconditionals mean that if one true, the other one has to be true as well. So this one's true, but that one's not. That's false. In other words, you've been to New York City, but not the most populated city in the United States. Wrong. New York is the most populated city in the United States. But all we're really paying attention to, even if we take away the New York City context, is whether or not our entries match. So P and Q, those are different. The biconditional is false. And P and Q, those match. The biconditional is true. And that's the key to a biconditional. Biconditionals just mean, do the conditions match? True and true, that's a true. False and false, that's a true. But true, false, or false, true, those are both false. Our conditions don't match, and so we get false results on those. And a biconditional is generally an easier one to understand than a simple conditional statement. But the next thing I want to do is show you that sometimes the truth tables can reveal that there's simpler ways to write logic statements. So let's do that now for this one. Let's make a truth table for P implies Q and Q implies P. So for starters, we're going to have P and Q. Those are our simple statements. And of course, we'll have the normal conditions on those. True, true, false, false for P, and true, false for Q. That ensures we see every combination of conditions for those two simple statements. Now, our final statement that we want to build, we're going to put on the far right. And so we're going to have P implies Q and Q implies P. Now we can't judge whether this conjunction, this and statement is true unless we can look at these two columns. So that means we have to build a P implies Q column and a Q implies P column. So we'll do that right here. So let's start by building our P implies Q column. Remember, P implies Q is true whenever P is true and Q is true, or if P isn't true at all. So P implies Q, true implies true, that's true. Row 2, P implies Q, that's false. We have P but not Q. Q did not follow P, and so that one's false. And rows 3 and 4 will be true because this is, remember, if P then Q. Well, we don't have P, so it doesn't matter. And so those are both true. Now let's do the same thing for Q implies P. Does Q's truth implies P's truth? It sure does in row 1. In row 2 we have a false statement, so if we don't have Q it doesn't matter whether we have P. That's true. Row 3 we have Q, but we don't have P. Q does not imply P here. That one's false. And then in row 4, Q is false, so it doesn't matter whether or not we have P. That will be true. Now we want to make a column for the conjunction P implies Q and Q implies P. In other words, they both have to be true in order to get a true result in this column. So here we go. We're comparing P implies Q and Q implies P. Both are true. That means the conjunction is true. Here, only one of us is true. The other one is not. And so that one's going to be false. And in row 3 here again we have one true but the other one is false. Conjunction means we would need them both to be true. That one's false. And in row 3 they're both true. We have a true statement. Now the thing I want you to notice here, we got the result true, false, false, true. Just a little bit ago when we looked at the biconditional, remember the biconditional was P if and only if Q, gave this exact same set of outcomes. True, false, false, true. And what that means is that the biconditional, P if and only if Q, is the exact same statement as P implies Q and Q implies P. And that should kind of make sense. If P forces Q to be true and Q forces P to be true, then they're forcing each other to be true. In other words, if we move one direction and the other direction, then we must have a biconditional and we get the same result. So there's really never a reason to write an expression that complicated when it can be written in that much simpler way. Here's one for you to try for practice. Create a truth table for this logic statement. Not P implies Q, biconditional with P and Q. Go ahead and set up your table and unpause when you're ready to see what that table should look like. Okay, so here we go. Okay, this time we want to check the biconditional. Not P implies Q with P and Q. So we're going to start our table the same way. P and Q, normal conditions. The compound statement that we want to check we put on the far right. Now let's build the columns we need to test this one before that. So if this is the one that we want to test, we need to have a P and Q column, and we have to have a not P implies Q column. So to the left of this we'll put a P and Q column. That's one of the things that we'll need to test. That'll give us that information. Now we need a not P implies Q column. That'll give us the information we need to test for our biconditional. But we can't really build a not P implies Q column until we also have a not P column. We have the Q column, but we need to establish not P, so we'll do that one right here. Okay, now if we build these intermediate columns, we can build the column to the right on our truth table. Here we go. The negation of P, well, we're just going to reverse all of P's conditions. So that'll become false, false, true, true. And now we'll check the negation of P implies Q. Let's do that. There's our conditional statement. So does the negation of P imply Q? That would be true since the negation of P isn't true to begin with. And this one, if we have the negation of P, do we have Q? Well, we don't have the negation of P, so it's moot. That's true. This one, if we have the negation of P, do we have Q? Yes, we do here. And our bottom row, if we have the negation of P, do we have Q? No, we don't. So that column is true, 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 false. Now we'll be able to transfer that over to here in just a minute. Let's check P and Q. P and Q is the conjunction. We need to have both of them in order to get a true result here. So P and Q, that's true. P and Q, nope. Below that, no. And below that, no. So we have true, false, false, and false. Now we're ready to use those two columns to check our biconditional statement. Remember the biconditional, the double arrow, yields a true result if these two match, if they are the same. That is to say, one is true if and only if the other one's true. So here we go. Yep, those are matching, so that one's true. Here we have one but not the other. That makes the biconditional fail. Here we have one but not the other. That makes the biconditional fail. And here we have both fail, and that makes the biconditional true. Now what we've done here is we've asked ourselves, does this column, not P implies Q, and the P and Q, does this give us the same result? Well, we can see visually that it doesn't, but a biconditional checks that. It says they give the same result in row 1 and they give the same result in row 4, but they don't give the same result here. This is really a test as to whether the two halves of this biconditional are equivalent. If these two columns were exactly the same, then their biconditional results would be true everywhere. You're going to have a homework question related to that in your work for today. Now, one of the things I want you to notice as we kind of stumble our way through truth tables here is this really teaches your brain to think in a really logical way. There's only one right result, and it's sort of binary here, right? Everything is either true or false, but this is really teaching your brain to think in a really, really disciplined way. And that is the beauty of logic, and one of the things that a lot of people really struggle with, but it's this type of work that really develops logical thinking, and that's one of the reasons that we're spending time on this. Okay, here's one more for you to try for practice. Create a truth table for this logic statement. P biconditional with Q or the negation of R. Now we've got three simple statements here, P, Q, and R, so that's going to change the look of your table. See if you can set up and complete a truth table for that statement. Unpause to see if yours matches mine. Okay, well, here we go. This time we have three simple statements or three conditions, P, Q, and R. So as we saw in our previous lesson, that's going to change our combination setup. We're going to have 4 trues and 4 falses for P, followed by paired up trues and falses for Q, and alternating trues and falses for R. Now the conditional statement that we want to check, we're going to put on the far right like always. P if and only if Q, or not R. Now, what do we need to do to build that? Well, we're definitely going to need a P if and only if Q column. And the other column we're going to need is the negation of R. And that'll do it. Once we have the negation of R and P if and only if Q, then we can test the disjunction and fill in our last column. Here we go. The negation of R, of course, is just going to reverse all the entries for R. P if and only if Q, let's go test those. So we're checking to make sure that P and Q have the same truth condition here. True, true, that's true. True, true, that one's true. True, false, false. True, false, that one's false. False, true, that one's false. False, true is false. False, false is true, and false, false is, again, true. And now we're ready to check the disjunction. So we're looking for P if and only if Q to be true, or the negation of R to be true. A true in either one will make our entry true. Here we go. Row 1, we have a true. Row 2, they're both true. Row 3, we have neither of them true, so that one's false. Row 4, we have a true. Row 5 is false. Row 6, we have a true. Row 7, we have a true. And in row 8, they are both true. And so there's our final column. And so we're done with our truth table. So of course, you should be asking, well, what did these really get us? Well, for one thing, it really helps build your logical thinking and your analytical thinking. Two, it allows us to determine if following statements are equivalent, and sometimes it shows us that we can write equivalent statements in a simpler way, as we saw earlier. And three, it's going to allow us to do a little bit more with logic circuits in our next unit. But here's the last problem of this lesson. Let's use a truth table to determine whether these two statements are equivalent or not equivalent. That is to say, P or Q versus the negation of P and the negation of Q. That's kind of a mouthful. Let's set up our table. Okay, so we want to build a truth table that contains both of these columns. The first one, the one on the left, that's pretty easy. P or Q, we can build that one right off the bat. P or Q. We need either P to be true or Q to be true. So row 1, we have both. Row 2, we have one of them that's true. Row 3, we have one that's true, but row 4, we don't. And so that column is going to be true, 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 false. Now, we need to check our other logic statement as well. So let's build that one. That one's going to take a little bit more work. I'm going to move it way over to the right. We want to build the negation of P and the negation of Q. So before we can build the negation of P and the negation of Q, we need to build the negation of P and the negation of Q. Or in other words, we need to build what the prior statement is, not P and not Q. But we really can't build not P and not Q unless we know what not P and not Q are. So we have to build those columns. So we'll build a not P column and we'll build a not Q column. Those will tell us this result, and this column will tell us this column's result, and then we can compare our results. Here we go. The negation of P, we're going to reverse our entries for P, and those become false, false, true, true. The negation of Q will reverse our Q entries, and so those will be false, true, false, true. Now, our conjunction, we're checking, do we have not P and not Q? Not P and not Q? Nope, we don't have either one. Not P and not Q? Nope, that's false. Not P and not Q? Well, we have one, but not the other, so that's false. And our bottom row, not P and not Q? Yes, there we have both, and so that entry is going to be true. That allows us to complete our final column here, the negation of not P and not Q, or in other words, the negation of this column. So false, 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 true will become true, 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 and false. And so we can see now when we compare the two columns that we wanted to create, P or Q, true, 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 false, and the negation of not P and not Q, true, 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 false, they are always going to give the same results. So from a logic standpoint, it's much simpler to say P or Q than it is to write this more complicated logic statement. Where are you sitting around writing logic statements? Well, we're not, but we are going to be looking at Boolean expression and Boolean algebra, and this provides the basis for that. We're going to see some applications of this in our next topic, but right now there's some principles that you're learning that are going to make that work a lot easier. Okay, well, there's a lot of information in that lesson, but they all started with this conditional statement. A conditional statement is that type of statement where if we have P, then we must have Q. That conditional statement is a little bit tricky. Make sure that you set that as your goal to understand as you're working through the practice problems. Out of those basic conditional statements, we have the three related statements of the converse that reverses our two simple statements, the inverse, which negates the two simple statements, and contrapositive, which negates and reverses our two original statements and is actually equivalent to the original conditional statement. And so being able to interpret those and understand what they mean kind of refines the distinction between different ways of stating if-then statements in your mind. And finally, if we have a conditional statement that's true in both directions, that is to say an if and only if statement, we have what's called a biconditional. And the biconditional is the easier one to understand. Biconditional statements are true when the truth conditions of our simple statements match. That is to say if they're both true or both false, and only if they're both true or both false. If they don't match, we get a false outcome on the biconditional statement. Now, we're not done with logic, but we're going to take a little bit of a turn and apply this in a different way and start looking at some of the properties that we've established in our next lesson. So as always, make sure to let me know if there's concepts here or homework problems that you have trouble with. I can help you understand those a little bit better, and we'll see you in the next lesson.